There are four concurrency phenomena associated with a given triangle. In this video, we're going to take a look at the first two of those. Namely, we're going to look at the concurrency of a triangle's perpendicular bisectors, and then also the concurrency of a triangle's angle bisectors. We won't prove these results in this video, but we will talk through some of the ingredients that might be necessary to prove these. First, starting with the perpendicular bisectors of the sides of a triangle, in order to prove concurrency of those three, we're not only going to need the definition of what a perpendicular bisector is, but we're also going to need a consequence of that definition that's going to help us to prove concurrency. This is something we'll see happen for all of the concurrencies that we study in this chapter. So what we're going to do is first give the definition of what a perpendicular bisector is, and then also give an argument for a consequence of that definition, so something else that characterizes perpendicular bisectors. So the perpendicular bisector of the side AB in the triangle ABC is a line, we'll call the line L, and that line has to meet the side AB at a right angle, so be perpendicular to the side AB. And then the point at which it meets the side AB, if I call that point P, will be equidistant from A and from B. So AP and PB have equal length. So this is the definition of what a perpendicular bisector is. It's perpendicular to the side AB, and it meets that side at a point which is equidistant from A and from B. But in order to prove concurrency, we're not only going to need this definition, we're also going to need a theorem, which is a consequence of this definition, another way to characterize the perpendicular bisector of the side AB. So we're going to look at that next. And the consequence that we're going to use is this one. It says that all points on L, if L is the perpendicular bisector of AB, then all points on L are equidistant from A and from B. So by definition, we already knew that the point P, where the perpendicular bisector meets the side AB, has the same distance from A as it does from B. But according to this consequence, this theorem, any other point that I pick on this line will also be equidistant from A and from B. So if I pick a point Q, which is on this line, and I draw the lines from Q to A and Q to B, then those two segments from Q to A and from Q to B will have equal length as well. So the perpendicular bisector of AB consists exactly of all those points in the plane, which are equidistant from A and from B. That's an alternative characterization that we're going to end up needing to use rather than just the definition of perpendicular bisector when it comes time to proving concurrency. But if we can prove concurrency, then we get something really cool. Concurrency will mean that the three perpendicular bisectors associated with a triangle, so the perpendicular bisector of AB, the perpendicular bisector of BC, and the perpendicular bisector of AC, that those three lines will meet in a common intersection point. That's the kind of concurrency that we mean here. And that common intersection point is a concurrency we're going to call the point O. And because of the alternative characterization of perpendicular bisector, namely that the perpendicular bisector of a side consists of all points that are equidistant from both vertices in that side, we also know that this point, which is concurrent to all three of these perpendicular bisectors, will have the same distance from A as from B because it lies on the purple line, but also the same distance from B and from C because it lies on the green line, and the same distance from A and from C because it lies on the orange line. And so that point is equidistant from all three of the vertices of this triangle. Because of that, we can use that point as the center of a circle which passes through all three of the vertices of this triangle. So the point O is called the circumcenter of the triangle ABC, the concurrency between its perpendicular bisectors. And it's the center of a circle that we call the circumcircle of the triangle ABC. It's the circle which passes through all of the vertices of the triangle A, B, and C, and which has this concurrency point as its center. And finally, we say that that circle has been circumscribed about the triangle ABC. So there's your vocabulary lesson for the concurrency of perpendicular bisectors associated with a triangle.